Hello, taking a look at chapter 3.7, the derivatives of inverse functions. All right, so before we really get into how to do the derivative of an inverse function, let's just kind of remember what an inverse function is. All right, so this f negative 1, all right, that negative 1 almost looks like an exponent, stands for an inverse, the opposite. Okay, so usually f of x means you plug in an x value, you get out a y value. Inverses, yes, it'll say f inverse of x, but really by putting a number here, that's truly a y value, all right? And we are then finding the matching x value, okay? So to do this with an entire equation, to find an inverse, typically we have to restrict domains. If you recall, inverse functions have to be what is called one-to-one. Meaning if we just graph our function, what was that? Squared minus 3. That's what it was. It was. All right, so if we graph just this function, we can take its derivative wherever we want to. That's fine. All right, but the thing is, this function, would not have a true inverse because it is not one-to-one. It does not pass the horizontal line test. Okay, but by limiting the x values, I don't know if you remember seeing this, it said x is greater than or equal to 0. By limiting those x values, we've cut out the left side of the graph and we only have this group. We do in fact have an inverse. Okay, it is now one-to-one. All right, so to find the inverse, the opposite, you switch. Remember, this is like a y. You switch the x and the y in your equation. You then solve for y. So we would add the 3. You would then take the square root. All right. And once you've gotten y by itself, we just call that the inverse. Okay. So we can find the inverse function of a square root. Or I'm sorry, of a squared. Or a square root. We can do either one of those. Now if we graph this, now I've got to call it G just because I've already labeled that X or F. Yeah, it was a plus. You'll see that we do in fact have this inverse. Now the idea is any value in our original function, like 2, 1, will be represented in our inverse, 1, 2. All right, x's become y's, y's become x's, and we have this, line of symmetry through the middle. This line y equals x. All right, this was all Math 171. This idea of being able to find this inverse and be able to use it. All right, but if I have this function and I want to know the derivative of this function, okay, well, it should make sense that the derivative of this function and the derivative of its inverse have some form of collaboration between the two. I mean, it's really the same x values and y values, they're just in different orders. So how can we relate the derivative of a function and the derivative of its inverse? That's kind of the question. Well, to be able to do that, we found an inverse. Let's take its derivative and just see how it relates to the original function. Okay, so the derivative of the inverse, f inverse prime of x. Well, this is, instead of the 1 or the square root, we can say the 1/2 power. Okay, well, the derivative of that would be 1/2, 1 over, so I'm going to take away 1 from this, so it's going to be negative, and it's a square root. All right, so we have 1 over 2 square root of x plus 3. Okay, so we have our inverse function there. Okay. All right, the derivative of our inverse function. So we can find that using algebra, and then that's fine. But mathematics has kind of simplified this a little bit for us. It turns out we don't really truly need to find just the derivative of the inverse itself, as long as we know the derivative of the original function. Okay, what we can do is the derivative of the inverse is 1 over the original function's derivative with the inverse composed inside of it. Okay, so what I mean by that, finding the inverse and then taking the derivative was kind of a tough process, especially for some functions. Some functions, the original function, the inverse is easy to find, but its derivative is physically hard. So let's just take the derivative of the original. Derivative of the original is what? 2x. All right, so what this formula says is that f inverse prime, the derivative of the inverse, can be written as 1 over the derivative of the original function, 2x, but instead of this x, put the inverse function. So 2 times, and then instead of this x, wherever it is, replace it with the inverse of the function. The inverse of the function was the square root of x plus 3, which was very easy to find. And look at that. This answer, they are exactly the same. Okay, so instead of having to find the derivative of the actual inverse, we can just kind of use this little formula, and generally things go really quick. All right, this is a great choice for when the derivative of the original function is really easy. All right, you can take the derivative of this x squared minus 3, incredibly easy. But the derivative of, the square root of x plus 3 was definitely a little bit harder. Okay. I didn't even do the chain rule like I was supposed to. I was supposed to times by 1. The derivative of x plus 3 is 1. So it can definitely get a little complicated once you have the inverses of things. It gets messy. But this formula allows us to just do that really quick, really easy. All right. So again, if I have this formula, or this function, g of x equals x cubed, I can find the derivative of that very easily. Derivative of 3x of x cubed is 3x squared. Move the power in front and bring that down. Now, the inverse function is also very easy. All we would do is switch our x and our y, and then take the cube root, so it's really easy to find the derivative of the original. It's really easy to find the inverse of the function. But to find the derivative of this cube root is definitely a little bit harder. Okay, so what we can do is just follow this formula. 1 over the derivative, 3 times something squared, and inside of the derivative, take your inverse function and put it in there. And there we go. We have our derivative. Now, technically, we can move this squared to here. All right, you can put it inside, or you can leave it outside. Your choice. I think it looks just a little bit better if you apply that squared to the x instead of to the outside of that cube root. But it's totally fine. If we did just do the derivative of our inverse directly, so this is what? X to the 1/3. It would be 1/3 x to the negative 2/3. Move the power in front, reduce by 1. So 1 over 3. And then that exponent would go to the bottom. And that is the cube root of x squared. All right. So the two formulas, you can just do the inverse and then take its derivative. It will work for sure. But this formula for the inverse functions usually goes just a little bit easier. Okay. And especially if we start to look at things like this. If we have sine, all right, and then sine inverse. Now, I know the derivative of sine. I can do that very quickly, very easily. But I have no idea what the derivative of sine inverse is. That is not something that we know. this -1 that's on the sign, that is not an exponent. That's not like a chain rule type of problem. That is not that. Not what that means. That -1 means the word inverse. Okay, so I can't really just apply a chain rule. I can't apply a power rule. That is not something that we have the inverse for. So that's why we truly can use this formula we just worked with. The derivative of an inverse function is 1 over the derivative of the original with the inverse inside of it. Okay, so the derivative, 1 over the derivative of the original. Derivative of the original is cosine of. Then we take the inverse and we put it inside. So that is our inverse derivative. All right, 1 over cosine of sine inverse. Okay, and so that technically is our answer. All right, so the general idea, if you remember your trigonometry work with cosines and sines and inverse of these things, the idea is normally you put an angle into sine and you get some number out. Okay, so an inverse means I know the number and I'm finding an angle. Okay, so what this would do, 1 over cosine of sine inverse. If I put a number in here, I'm going to have to put in my x value has to be like a value, like a number on the unit circle on the outside. Okay, now inverse of that is going to create an angle. Okay, so sine inverse of some number is going to give me an angle back out. So I've got an angle from this. I then do cosine of that angle, and that will be the slope of my tangent line. Okay, so think of it like, on the unit circle. Let's say I have this point on the unit circle, and I want to know the slope of the tangent line at that point. Okay, so I have to know a y value. That's what sine inverse tells you, is a y value. If I know a y value, it will then tell me the angle. I can then do cosine of that angle, cosine of x value. All right, and that will tell me the slope of my tangent line. Okay, so putting this all back together with your trigonometry review. All right, but since that is kind of weird to do sine of cosine inverse, we can kind of rearrange this with some fun little pieces. All right, if we say that our angle theta is from sine inverse, so if theta is here, all right, sine, if you remember, on a triangle is opposite over hypotenuse. So if theta is sine inverse, that means if we rearrange, x equals sine of theta. So we can make this x over 1. So it means the opposite is an x and the hypotenuse is a 1. Great. Can you find an expression for the adjacent side? Well, yeah, it's a right triangle. So I can do the Pythagorean theorem. A squared plus x squared equals 1 squared. So this side, 1 minus x squared, and then take the square root. Cool, I can do that. All right, so now to put this back together, do you remember how we just said our inverse derivative of sine was 1 over cosine of sine inverse of x? All right, so the nice thing is that this can kind of put this all back together and not have these sines and cosines and the inverse then in here anymore. All right, sine inverse, the idea is sine inverse gives us an angle. So we have cosine of some angle. Okay, now cosine of an angle, whatever angle it is the adjacent over the hypotenuse. Well, so we have 1 over the adjacent over the hypotenuse, and divide by 1 just stays the same. And so that actually allows us to get this thing, 1 over the square root of 1 minus x squared. So if we know an x value, we know just some value, We don't have to, plug it into sine inverse to find an angle and then plug it into cosine to get the value. We can just go straight to this, all right? 1 over, because of that formula for an inverse. And then the way we find a cosine value, if we know an opposite and the hypotenuse is 1 minus x squared inside of a square root from the Pythagorean theorem. Okay. So the derivative of the derivative of sine inverse becomes just this wonderful little formula, 1 over the square root of 1 minus x squared. All right, and that's kind of where this leads us. This wonderful formula allows us to get there. All right, so if that's the case, we can then do a cosine. Okay, we know the derivative of cosine is negative sine. All right, the derivative of cosine inverse then is 1 over the derivative of our function. Inside of it, we put our inverse function. Now, on that same kind of triangle idea, cosine inverse of x should give us an angle. Now, it's just an x inside of here, so that's like x over 1, which means our opposite side then, the same way, find that Pythagorean theorem, a squared plus b squared equals c squared. So we have the square root of 1 minus x squared is that opposite side, that vertical side. So cosine inverse should give us an angle. That negative can just move to the top. And sine of this angle is the opposite over hypotenuse. So it's pretty much the same exact answer. It's just this negative on the top. All right. So the derivative of sine inverse is a positive. The derivative of cosine inverse is a negative, both the same fraction, which should make a little bit of sense. The derivative of sine is positive with cosine. The derivative of cosine is negative, all right, with the sine. They're very similar answers, one positive, one negative. Now, we can use these things to then find the derivative of tangent and cotangent, secant and cosecant inverses. All right, notice they have similar setups, 1 over, all right, and then that fraction. Okay, so these formulas, all right, are just formulas. If you're doing the derivative of tangent inverse, all right, we can just plug it straight into this formula. Right, same idea. We don't really need to repeat that whole process, this whole right triangle trigonometry idea. We can go straight to these formulas, straight to this formula or this formula now, all right, when we do the derivative of an inverse sine, cosine, or tangent. Okay, remember, inverses are finding angles, and you do actually do that on your project in this module. Finding the derivative of an inverse, I think we use tangent in our project. All right, so good luck with that, and good luck on your math work.